We spent an awful lot of time in the first 2/3 of this course talking about the acceleration due to gravity. Everybody knows that if you hold a mass near the surface of the Earth and you release it, it will fall with an acceleration equal to 9.8 meters per second squared. That is to say, its velocity will increase by 9.8 meters per second for every second that it falls. We look for an explanation of that, and we find it in Newton's second law. It's caused by the force of gravity. The force of gravity causes the acceleration, and I can go around and solve lots of free fall problems. But it turns out that when this symbol G appears, here's the lowercase g, in our course we immediately think, well, 9.8 meters per second squared. That's what g is equal to. That's what you use to calculate. That's what you use in the lab. That's what you use to describe the acceleration due to gravity. But in more advanced physics, I guess in a sense we're going to grow up today a little bit, and our physics is going to become more sophisticated. The physicist calls this quantity the acceleration due to gravity, not the acceleration due to gravity. The physicist calls this quantity the gravitational field strength. Ooh, that's fancy. The reason why this idea exists is that while it's true that I can hold up a mass and release it and it falls, look at it go, we all appreciate the fact that the effect of gravity, the phenomenon of gravity, exists everywhere all at once. There's gravity all around us, at every place in this room, every place on the surface of the Earth, and beyond, even if nothing observable is happening. You don't need a thing to be falling freely for the gravity to exist. It always exists, everywhere. Now you'll notice that I put a harpoon on top of my G here, and the reason why I did that is to make sure of a thing that we already knew but didn't have a lot of use for. Gravity's a vector. Downward, right? Very reliable. Gravity's not too fancy. Everywhere you go, gravity downward. You have to be careful. Expand your thinking a little bit. Sure, in this classroom, gravity downward, but at large, literally, the Earth, gravity is actually toward the center of the Earth. Straight downward is an idea that we have just because the Earth is so large that small regions of the Earth where we live are relatively flat. Gravity toward the center of the Earth. Gravity has a magnitude and a direction, so it's a vector. It's a vector that exists everywhere in space and time, all at once. It's a quantity that we call a field. Specifically a vector field, but a field is a vector quantity representing a natural phenomenon, like gravity, or in today's discussion, like electricity, that has a value everywhere in space and time. An idea that always occurs to me when I think about fields is a field of grain. Imagine beautiful sunshiny day, a little breezy, nice and cool, and there's grain. Maybe it's wheat, something like that. Every stalk has a different length, the magnitude. When we represent vector quantities with arrows, the length of the arrow is the magnitude of the thing. And the direction the stalk points is the vectorness of it, the direction of that vector quantity. And as the breeze blows naturally across the field, it's lovely to imagine how calming. And the grain sways this way and that. The magnitude and the direction changes everywhere in the field all at once. A field of grain, a field of vectors, arrows, pointy arrows that change in magnitude and direction everywhere in space. A vector field. Now gravity's super simple. How does the vector field of gravity work? Well, the gravitational field points toward the center of the Earth. It's really not that exotic. Now, next to G, I wrote its units. Oh no, Shadi, you made a mistake. G's in meters per second squared, as in 9.8 meters per second squared. No, it's not a mistake, because the force of gravity is equal to m times g. If I solve that around, g is equal to the force divided by the mass. And I measure the force in newtons, and I measure the mass in kilograms. So alternate units of g that I never mentioned before, newtons per kilogram. Oh, that's weird. Nobody says that. It's true. Nobody says that. But alternate units for g could be newtons per kilogram. I mentioned in our last session that there are ways in which gravity and electricity are the same. And I specifically pointed out that Coulomb's law that I use to calculate how much electrical force I should expect in any given situation has the same mathematical form as the law of universal gravitation invented by Newton. There are similarities between the two. Well, I'm going to push my luck on that idea and talk about a thing that you already know. The force of gravity is mg. That's not a new thing. The force of gravity is what we call the weight. And the weight is the mass times g, and you knew that already because you've done it a bunch of times in calculations for this class. Physics students are so familiar with this. It's almost like that the weight of a thing is mg is almost like our physics version of the biology concept, the mitochondria is the powerhouse of the cell. Everybody knows that. The weight of a thing is equal to mg, but now I want to think about it differently. It's fine to think about this as mass times acceleration. That's very familiar. That's Newton's second law. But instead, let me think of it as a property of matter that is the mass. And that property of matter interacts with the gravitational field. An intimate association between the inertia of an object and its relationship to the gravitational field. Ooh, the physics sounds fancy all of a sudden. Well, it does. And that is going to be useful to us, but let's not lose sight of the fact that, yeah, it's just mg, it's your good friend, gravitational force. Well, I said that there was a property of matter called inertia and that the mass was the measure of that quantity. Now I'm saying that there's a property known as electrification, or electricity if you like, and the measurement of that quantity is the charge. So is it possible that the electric force, which I already know how to calculate, that the electric force is equal to the property, which is the charge, interacting with a field? Not a gravitational field, but an electric field. Indeed, it's true. I'm going to use capital E for electric field. Shadik, capital E is total mechanical energy. Yeah, I know. There's lots of nature out there and only a few symbols to go around. You already know we've been recycling symbols. Capital E, in this context, the electric field. A vector, it has a magnitude and a direction. In both of these equations, I left the harpoons out because for us, I think the harpoons are a little bit fancy. But these are both vector equations. The electric field is a vector. The electric field, in fact, is the vector force per unit charge everywhere in space and time. When I went about calculating some electric force, I had to take a charge and put them near each other so I could say that there was an effect of attraction or repulsion. I had to actually set something up in order to see the electrical effect. Just like if somebody says, prove to me that there's gravity, which is a silly assertion to make, I'll hold up an object and drop it. And you say, see, there's a force that causes an acceleration. No, what I'm saying now is just like gravity, the electric field exists everywhere in space and time all at once. This room is full of gravity. It points downward. This room is also full of electric field. The electric field is not so simple as gravity. The electric field in this room points every which way, and its magnitude changes dramatically. The electric field can be quite complicated. But I want to calculate how much electric field that I have. It's really a simple proposition because the electric field is the force per charge. The electric field is the force per charge, and I know what the force is. Yesterday, I calculated electrical forces, K, Q1, Q2, over the distance between squared. So if I take my force and I divide by a charge, there's a little question, which charge am I dividing by? Am I dividing by Q1 or am I dividing by Q2? Well, it doesn't really matter because one of these Q's is going to go away. Thinking about it in the context of gravity, when I talk about the gravitational field in this room, what created the gravity? Well, the Earth did. The Earth did. And it's the mass of the Earth, it turns out, that creates the gravity. So when I divide my force equation by Q, the Q that's left over is the Q that is creating the field. The electric field is equal to KQ over D squared. And you say, Shadi, it's practically the same equation as the force. It's practically the same equation as the force. Why do I need electric field at all? Let me just calculate the force. The electric field is practically the same thing. Well, the fact of the matter is, in everyday life, the only gravitational interaction that matters in our everyday lives is the gravitational interaction with the Earth. If I have you do a laboratory and I give you a 200-gram mass, that mass has a weight that is the gravitational force exerted on it by the Earth. And that's the only issue. You yourself exert a gravitational force on that mass, but it's so small that it doesn't matter. The planet Venus exerts a gravitational force on that mass, but it's so small it doesn't matter. The gravitational force scales in such a way that near the surface of the Earth, the only gravity that matters is the gravity of Earth. That's not the case when I solve electricity problems. In my lab or in my engineering, if I'm trying to leverage the electrical effect to create technology, in any given case, there are trillions of charges involved. And all of those charges are exerting forces on all of the other charges, and it becomes impossible. You saw me do a demonstration where I calculated the force between two charges. Well, that's easy. Try calculating all of the forces between trillions of charges. It can't be done. Let me give you a small idea that might help you consider why this is valuable. Let's say we have an interest in the economics of the United States, particularly the earnings of American citizens. Now, I could say, well, I need to understand about American household incomes. So I'll consider that Jose earns this much, and Mary earns this much, and Mohammed earns this much, and Dave, well, now this is going to be a problem. There are millions of Americans. Describing it in the context of the earnings of every American is bonkers. What do we do instead? Per household. We describe it per the individual quantity. That way you've got one number that describes the whole thing, instead of a trillion numbers that you then use to describe the thing on average. It is way more convenient to talk about the force per charge in space and time than it is to work out what all the forces are. And it turns out to be true as well, as a side bonus of the whole thing, that if you choose to describe things in terms of the electric field instead of the force, there are natural patterns that lead to equations that greatly simplify the calculations. We're not going to use any of those equations in this course, but you've seen those equations written up here on the window when you're looking out on a sunny day, trying to imagine being somewhere other than in physics class. Electric field is useful. The electric field is the force per unit charge. Well, the force is measured in newtons and the charge is measured in coulombs, so the units for electric field will be newtons per coulomb. That is very unfamiliar, but it was unfamiliar when I said that G might be 9.8 newtons per kilogram. That's weird, nobody says that, but it's the same thing. It's the amount of force that I get per property. Newtons per coulomb, the unit of electric field. Now I have an equation, I can calculate how much field there is everywhere in space. It's pretty great. But I don't know what I'm calculating because I can't see the electric field, I can't smell it, I can't taste it. It's difficult to visualize because human sensation has no access to the electric field. Before we finish and start calculating some stuff, let's just have a shot at visualizing. Here, I have drawn a positive charge right here, smack in the center, and I've called it capital Q. It's okay to call a charge capital Q. It's allowed. We use lowercase most of the time for Q. It's okay to use a capital Q, and I'm using a capital Q here because it's the charge of interest. It's the charge that I'm talking about. It's the charge, and here's a vague statement, it's the charge that creates the electric field. If I just put that charge there, it would be blank everywhere around. You wouldn't see anything. So I draw what are known as electric lines of force. The electric lines of force effectively show me what the electric field looks like in the vicinity of this charge, capital Q, positive charge. Now, the electric field exists everywhere. If I were to draw lines to show all the field, I would have to completely black out the region. I'd have to draw an infinite number of lines because the electric field is everywhere. So what I do instead is I choose to draw lines, just a few, just 8, so that I can get a sense of what the electric field looks like. And this is what the electric field looks like in the vicinity of this charge Q. It is spherically symmetric and radially outward. Remember, electric field is a vector, so it has a direction. And in this case, I put arrows on my electric lines of force to indicate that the direction of the electric field is away from the charges. That seems completely arbitrary. Like you just made that up. You just chose that that was true. Well, I didn't choose. Ben Franklin did. When Ben Franklin chose to assert that vitreous charge was positive and resinous charge was negative, this decision was made. Positive charges are the source of electric field. Do you see how it looks like the electric field is spraying out of the charge? Well, that's not true. The electric field is static. It's not changing in time. It's not shooting out. But it turns out that thinking about it that way doesn't do a whole lot of damage to your understanding. The positive charge is the source of electric field, and out it goes. Notice that in order to move away from the positive charge, the lines have to get further and further apart. It turns out to be generally true that when electric field lines are close together, the electric field is strong. And when electric field lines are far apart, the electric field is weak. And so my diagram here implies that as you go further and further away from the positive charge, the electric field gets weaker and weaker, which it does, because the electric field goes as 1 over the square of the distance. And this diagram matches that math. I can't see the electric field, I can't smell it, I can't taste it. The only way that I know that it's actually there is to reach into my pocket and take a little positive charge, positive plus Q, and place it right here in the field. When that little plus Q is there, it's going to feel a force that way, in the direction I've indicated with the force vector on the diagram. How do you know? I don't need any math. Capital Q is positive, and my little test charge is positive. They repel. They repel. That's fact. And so this little test charge is going to feel a force away from the positive charge. Away from the positive charge. Now, that's going to work every time that like charges repel. But I can generalize that and say the same thing in a different way, and it's kind of important. Positively charged particles experience a force in the direction of the field. That's saying the same thing as two positive charges will repel. That's saying the same thing. A positive charge experiences a force in the direction of the field. That's important because just like with electric force, where I said I can use my reason to work out the direction of the force without calculating anything, it's also true that for electric fields, I can use my reason to work out the direction of the force without doing any calculations at all. So it's kind of an important idea that I have this sense of the rules of the way things behave. Because if I could not see the charge Q, and I only knew that there was an electric field and a charge, I wouldn't know anything about attraction or repulsion. What I would have to do is reason out how this charge is going to move based on what the field looks like in its vicinity. The little charge Q looks at its feet, senses the electric field, and acts appropriately, moving in the direction of the field. We know that the electrical effect has two senses, the positive sense and the negative sense. So I need another diagram. For when I'm considering a negative charge, Shouty, it looks like exactly the same diagram. Yeah, but it's not. Do you see how the arrows are opposite? Do you see how the arrows are opposite? They go inward, as if the electric field is going to the negative charge. The negative charge is the sink of the electric field. Shouty, why? Because Ben Franklin made a choice a long, long time ago. The electric field goes toward the negative charge. And where the field lines are close together, the field is stronger. And when the field lines are further apart, the field is weaker. But if I take my little test charge positive Q and I place it there, what happens? Since the electric field is going toward the negative charge, positive Q experiences a force toward the negative charge. But I already knew that, because I know that since it's a positive and negative charge, it will be an attractive interaction between those two particles. But still, the positively charged particle moves in the direction of the field. By the way, this analogy between gravity and electric field really hits home here, because I could take this same diagram and repurpose it. I would just delete all the text. And in the center here, where I have a negative Q, I would put capital M sub E, the mass of the Earth. And the lines of force drawn on it would be the lines of force representing the gravitational field. The gravitational field of the Earth and the electric field of a negatively charged particle are identical. Identical. The patterns of the universe repeating themselves. It is a very, very beautiful thing. The electric fields in this room are very complicated. We are surrounded by the wires in the wall, the internet signals, the cell phone signals. The fans are generating electric field as they run, the lights are. The electric field in this room is very complicated. Electric field gets very complicated very fast. So I'm going to welcome you to not draw this next diagram. You can leave it out of your notes. But I am curious, what would it look like if I put a positive charge and a negative charge close to each other? What would the electric field look like in that case? Well, it's the vector sum of the electric fields, and this is what it looks like. Now, at first, it's like, blah, so complicated, except it makes an awful lot of sense. Notice that every electric field line starts on the positive and goes to the negative. Positive charges are the source of electric field, negative charges are the sink of electric field. The line in the middle goes straight from the positive to the negative, and that doesn't surprise me. If I were to place a positive charge in the middle, it would run away from its like charge and toward its opposite charge. Makes perfect sense. Where things get strange is out here in the middle of nowhere, where there are two electric fields to consider. The electric field due to the positive charge, which I've called E plus on my diagram, and the electric field due to the negative charge, which I've called E minus on my diagram, and I have to do vector addition to add them together to get the total electric field at that point. And the same thing happens at every point in space, everywhere in the region surrounding the charges. Things get complicated very quickly. I want to make a plea for physics here. The only reason why the physics just got super complicated and super mathy all of a sudden is that I have added many charges at once. The problem has become complicated. The physics of the problem remains very, very simple. The ideas are very, very simple, and the same ideas apply in the complicated situation as applied in the trivial situation, because things just get complicated. I have to wonder after this what happens. Just one last wonder, if you don't mind. What would happen if I took two positive charges and put them in the vicinity of each other? Well, I've got a diagram for that. Do you see how, and I don't really mind this, these two positive charges repel each other? Yeah? Doesn't that kind of feel when you look at the field lines? Can you not get that they give each other the ick? That they are against, it's kind of like they push apart. Can you see it in the field? Do enough calculations, use enough fields, see enough diagrams, and you start to get kind of a feel for the way the unseen electric fields behave everywhere in space and time. I'm really grateful because you guys are an excellent audience. You have no idea how shitty my performance was during second block. I like that a lot. I'm very pleased with that. So as long as the thing didn't accidentally stop in my pocket, it's going to be a good day for me. I'm struggling a little bit. You know, you go through those phases where like everything goes wrong.